Hello, everyone. My name is Hussein Lutfi, and I run the performance engineering team at Verizon AnyCast. I'm here to talk about the challenges that we had when we initially testing our network for IPv6, the problems we found, and possible solutions to those problems. Since this is the first time that we're presenting at NANOG, I have 2 slides to explain who we are and what we do. AnyCast is a content delivery network with presence in more than 40 locations around the world, and it's rapidly expanding. We have a small object and large object static delivery platform. We also have a dynamic object delivery platform, which has a lot of TCP optimizations in it. We do streaming and DNS, and as you might have heard, we were recently acquired by Verizon. Here's what my team does at AnyCast. We're a bunch of full stack engineers that look at mountains of performance data, and we try to come up with ways that we can make the CDN faster. Basically, we're up against what Einstein predicted, right? We can't go faster than the speed of light. We're coming up with different ways to deliver the objects faster. And what we're going to do, what we're doing is that we look at the entire stack. And what it makes it really interesting is that one day we focus on kernel, file system, TCP. The next day it's application optimization. The day after that it's network and AnyCast optimization. And we had several cases that we actually had to do physical changes in our data center to improve performance. And so basically, whenever there's a complex case coming up and no one else can explain what's going on and it touches multiple areas, it's the performance engineering team that gets involved to be able to address those issues. In my talk, you're going to hear a lot about response times and milliseconds. And let me just quickly explain why it matters so much. There are a lot of independent studies that measure the CDN performances, and they actually publish the data publicly. And if you look at one of these benchmarks, this is Sodexis data, the difference between the best performing CDN and the worst one in US is only 17 milliseconds. So that's why every millisecond counts. That's why we're so anxious to be able to cut round trips and minimize the internal latency of our applications. All right, so in my talk, initially when I submitted the talk to NANOG, it was talking about Path MTU problems and the solutions around it. The feedback that I got from the program committee was that it's good to explain how we discovered those issues as well, because there might be more interest in the audience to know about our experience with testing our network for IPv6 compatibility. So let me start with that. Whenever we launch a new product, what we do is that we have a tool set that we go over these tool set to be able to make sure that availability is what we expect and the performance is good. I'm going to walk over all of these steps and explain how we use these tools to detect IPv6 problems. Our target launch was IPv6 launch day, so we had a set deadline that we had to make sure everything is good by that. Normally when we launch a new platform, the first thing we test is synthetic monitoring. These are servers around the world, very well managed, very well peered, and we love synthetic monitoring because it's reproducible, it's controllable. When we have a new idea that we want to test, usually the first thing that we start testing is a synthetic test, because generally the random noise over internet is not present in these platforms. So we can rely on the data that we were collecting from these servers. We had a lot of synthetic nodes before IPv6 launch, but the problem is none of them were v6 capable at that time. So synthetic monitoring wasn't really an option for us. To this date, one of the platforms, 2 of them actually support it, but there's still not that good of a coverage. So the next tool that is usually available to us is ROM. Real user monitoring is a very clever idea that what they do at the end of the web page browse, what happens is that the web page becomes your test platform. And the user browser is going to call multiple objects from different CDNs and report the timing back to a central server. There are companies out there who are basically offering this product. You can get the raw data. You can get a lot of analysis from these platforms. The problem, again, let me mention the value of these ROM platforms, because now you can see visibility into areas that you had no visibility before. An interesting case, we were getting reports from one of these ROM platforms that our response time in Albania for some reason is 40 milliseconds higher than the best CDN in that country. And we're really curious what's going on. There was no synthetic node in that country, so that was the only indication that something is wrong. So we looked at it and we discovered the GeoIP mapping problem, and then once we were able to fix that, we were able to match the performance of the other CDN there. ROM, just a general caution, is that the data is full of noise, so we don't look at ROM data in real time. We don't set real-time alerts on these things. We look at ROM data mainly for trending purposes. What you're seeing in this chart is one of the TCP optimizations idea that we had. The blue line is a target line. You can see that when we applied to the red chart, the throughput goes up. And just to prove that it was our TCP performance optimization that made things better and not any other random effect, when we turned it off, we went back to the control set where we used to be before. But again, the problem with the ROM at that time was that they were not IPv6 capable. And none of the platforms, to my knowledge, today are. So that wasn't an option for us. We had to skip to the next option, which turned out to be really amazing. These little probes that RIPE distributed was extremely helpful for us. RIPE, I'm sure they've presented this before, and you guys are all familiar, but I'm going to explain how this probe helped us to find IPv6 problems. They have pretty good coverage around the world. They now more than 4,000 nodes that are deployed. And what we really like about Atlas is that it's completely programmable. You can set your test using APIs and get the result back from the APIs. They can do ping, trace, DNS, SSL certs, and they're doing HTTP tests in beta now. One of the cool things that you can have on Atlas, this is not available to all Atlas users, and RIPE will be probably really mad at me by telling you this, but the beta testers of IPv6 network had access to a certain tool that could actually launch v6 pings and traces from their entire network. And they'll give you the AS mapping and the AS graph. And on the graph on the right, I'm not sure if it's visible enough, but you can actually see the failed paths, and you can actually see what was the last AS that you saw in the trace before going blank, going dark. So it was extremely helpful for us to detect to zoom into the primary ASs that we had a problem with. All right, a general note is that we need more Atlas probes in US. It's heavily Europe-centric. I guess because RIPE started it, they have a ton of nodes there. But when you look at US, this is one of the largest US networks, and you can see that it's very East Coast-centric. The problem with this sort of deployment is that, especially for networks like us that rely on AnyCast, we need to be able to see the traffic, we need to be able to see the performance from around the country, not just East Coast heavy. So if you're thinking about launching a looking glass, I highly encourage considering Atlas instead. It will help the community much better. It's programmable. It can do everything that a looking glass can do with way less than risk of a traditional looking glass. But of course, it can't give you BGP lookups, which RIPE has a different solution for it. All right, so what did we learn from Atlas when we tested our IPv6 reachability? The first thing that we compiled was a POP to country mapping, and we drilled down to AS level and subnet level as well. And we tried to visualize the latencies. And then we uncovered pretty amazing things. One of the examples in this chart is that the country in the center of that chart is Ukraine. And you can see that it's going to two of our POPs. One of them is showing relatively good latency. The other one has high latency. So we wanted to know why part of that country is going to a different POP that is not the right location for it. And we focused on these high latency links first, and then we untangled the problems there. And this study is actually published by RIPE as one of the case studies of using Atlas. So we learned a lot from Atlas. We wanted to understand our availability, but we needed more data. That's why we launched our own ROM to basically test 3 different objects. We were calling a v4 object, a v6 only address, and a dual address, just to make sure to understand the availability of these 3, as well as the difference between the latencies. And we wanted to focus on the main problem areas. So one idea was that, okay, let's add a control set. Let's add IPv6 Google.com as well to be able to understand, are there networks out there that can reach to Google but fail to reach to us over v6? And that was the primary focus to fix these routing issues. We also did latency calculations. We knew ahead of the time that going v6 is actually, in a lot of cases, is not good for the performance mainly because of the peering policies that we have with all the networks. We have a very rich peering data set with all of you guys, but that's not the case for all the v6 connections. And we knew ahead of the time that there will be a performance hit. And over time, you can see this is a random AS that I plotted out. You can see that over time, we made it better and better. And that's an ongoing process at Edgecast. What we do is we look at these gaps between v4 and v6, and we try to come up with ways that we can close this gap. But it's a little bit more complex for us, I mean, resolving these issues, because we run AnyCast. And this is usually the way that I explain AnyCast. A cube made out of bulky bolts, right? And it's a stable system as long as you don't introduce a change. As soon as you add a new peer or remove something, the whole cube changes, the structure of your routing changes. So you have to be really careful about how to add a new player into an AnyCast mix. And that's why it's a little bit challenging for us, and time-consuming, I should say, to be able to fix all of the v6 peering problems. The biggest enemy of AnyCast is your own local prefs. I'm very excited to do this talk here because I looked at all the ASs that are present in this room, and we either directly peer with you or only one AS away. And in our daily optimizations, there are a ton of cases that whatever change or prefs that you guys have in your local networks are actually killing the AnyCast performance. And I'd like to go back to this topic maybe in another talk and explain what are the things that you guys can do to help improve the global AnyCast performance. All right, the last tool that we used, that we couldn't use, but is actually part of our used toolkit, is a TCP info. We internally call it the awesome TCP info because it gives the best value of looking at the behavior of internet at a global scale. What we do is that we first publicly discussed this in the last Velocity conference in New York. That's why I'm reiterating over that. Our chief architect, Rob Peters, had a very interesting talk about how we use the TCP info data. Basically, the idea is that at the end of the connection, we capture everything we know about that connection, all the packets that were transferred, the latency, the round trip, the number of retransmissions, all that stuff. And then we can do a deep dive into the global TCP performance. One of the things that we do with this data is that we map round trip based on the subnets. So if inside your network you decide to route one subnet in a different route than the other one, it will actually show up in our latency differences charts. And we know ahead of the time that, we know in near real time that you guys are making these changes. Countless examples, but we've had cases that, ISPs in Germany, they had a problem with the line card, they didn't know about it, but the latency that they introduced were completely visible in these charts, but none of the monitoring platforms of that ISP picked it up. We also we started doing some global internet health studies. This is an interesting slide. It's a little bit off topic, I have to skip really fast, but we detected a lot of a certain anomaly in the internet that some folks are assassinating the window scaling bit to slow down the internet. These are corporates that are not really happy about users having exponential growth in their TCP congestion window. And they're actually setting the window scaling bit on purpose. That's the optic at the end of the chart to slow down the connections. And we're planning to do a separate talk around this. This is very interesting. All right. Let me go back to the track of my talk. This is the problem that we discussed. We found a lot of sessions that were able to complete the v6 trace to us, but were not able to download the v6 object. And we were lucky enough to be able to do some packet captures, and we saw something really interesting. When we sent the initial congestion out, initial congestion window out. Only few packets were acknowledged, not all of them. We were getting feedback back from the client, but that was only for a few packets, not the entire transmission. Well, this is a clear sign of a Path MTU problem, because if you look at the trace again, you only see sub-MSS packets being acknowledged. None of the 1500 byte messages are being acknowledged. So that tells us there's probably a choke point, there's a black hole in the path that is not happy with us sending the full MSS. Well, the explanation is pretty simple, right? There has to be a V4 only internet that cannot route these packets, and someone had to establish a tunnel between these 2 points in order to make a uniform V6 connectivity between these two. But the problem with these tunnels is that when you send the 1500 byte packet out, the router, the beginning of the tunnel, has to inject its own header into it. When we send a 1500 bytes out, the router cannot inject anything more into the packet, so we'll actually send you a message that says, slow down, you have to lower your MTU. This is a known issue in the internet, and it had been addressed before. That's why the ICMP packet 2 big messages are for. So it shouldn't break the internet, and we're curious to understand, we're not filtering the message, we know that the ICMP is being sent out, why the connection is actually getting black holed. So we looked at the server that was handling the connection. It was in Frankfurt. The black hole session was in Frankfurt. We didn't see the ICMP packet. We looked at all the servers in Frankfurt. It wasn't there. So we launched a global packet hunt for that ICMP message, which is by itself is a very big challenge at a network at our size. But we managed to run that packet capture globally, and we found the packet. But we found it in Paris. It was very curious. The flow was in Frankfurt, but the ICMP telling us to slow down was arrived in Paris. Why is that? Well, the answer is inside the packet. When you send out the offending packet, let's call it, the one that is sending out that 1500 byte size, you're sourcing it from the AnyCast address towards the client. But when the ICMP packet is coming back, it's from a different source. It's from the router itself. And it happens in that scenario that the router itself was actually looking into a different routing table to make routing decisions for its own IP address. It was completely in a different routing table. So we have different peering policies. AnyCast behaves differently on different networks. So we ended up that the actual client to AnyCast flow was in Frankfurt, but the router to AnyCast flow was in Paris. We managed to fix that on this one instance. This was actually Hurricane Electric, and we were able to address this issue with working with them directly. But again, going back to the flow, the packet didn't arrive on the same server. It was delivered to Frankfurt, but not to the right server. So we thought that there must be something else going on there. We looked deeper, and we noticed that one of our systems, we have multiple layers of load balancing. One of the layers is doing a source destination based hashing. And what happens is that the load balancer looks at the source and destination of the packet to make the routing decision, forwarding decision. But the ICMP packet that is arriving is sourced from a different address, is sourced from the router address. So it will map differently to a different path. And it never makes it to the actual server. The solution to this is different from deployment to deployment. It depends on what kind of router or load balancer you're using. So I can't talk about specifics of your network, but generally, one of the ideas is that we have to look deeper and we have to look inside the ICMP packet to make forwarding decisions based on the offending packet, because the offending packet is actually a snapshot of it is included in the ICMP packet. All right, so how can we fix this and how big of a problem this is? The simplest solution is in the RFC itself. The RFC says that 1280 is the safest MTU in the intranet, so in the V6 intranet. So all the nodes have to be capable of transferring 12 messages with 1280 size. The bigger problem is that this is happening in V4 address space as well. The same problem that I just explained can happen in V4 as well, and it is happening. One of our synthetic platforms is Catchpoint. They recently launched a node in Iceland, and it was amazing because as soon as they launched the node, we received the ticket from them that it said, you know, we can't get to EdgeCast, we can't get to Yahoo, we can get to a lot of different sites. And it seemed that this is you know, first, it happens in v4 as well. And second of all is that there are a lot of folks out there that have this issue. So the suggestions that I have for you, I mean, the solutions to address this problem is different per implementation. But generally what I can recommend is that if you run an AnyCast network, look for these orphaned ICMP packets that arrive somewhere in your network with no matching flow. There could be sign of an attack, for sure, but if they're legitimate and you have a flow somewhere else in your network, this ICMP packet is telling you something that the actual flow is suffering from a Path MTU problem. The other idea is that you can set up last mile tests and compare your availability between AnyCast and Unicast. If going directly to the servers or going directly to your POPs shows higher availability than going to the AnyCast address, that's another indication that AnyCast routing is basically sending the packets, ICMP packets, to the wrong place. Another solution to this problem is MTU probing. This was deployed in Linux kernel a long time ago, and general idea is that they look for black holing signatures. If they see packets that are being acknowledged in the same way that I explained, what happens is that these packets, the systems will actually start lowering the MTU based on a set speed and try out those steps. It brings up your availability, but the problem is it will cost you your response time because the MTU tables are very aggressive, and you can see this TCP chart of that connection. It actually takes a long time to be able to ramp up and deliver the object. All right, that was my last slide. Thanks for your time. I'll be happy to take questions.
You can take questions now.
Leo Bicknell, Farsight Security. The root name server operators have been anycasting for quite a while, and there has been great debate over the years about the impact of anycast on that service. And they have investigated many of these, probably more focused in v4 than in v6. The interesting conclusions there is that, of course, the longer duration of your TCP connection, the more likely it is to be clobbered in an anycast world because of instability in the network, causing these return packets to go to the wrong place. And so the general thought is that if you're going to do anycast for TCP, you should do it for very short-lived connections. For instance, if you wanted to serve up a 600 megabyte ISO image or something, you would anycast a HTTP connection that was a 302 redirect to the server sitting right next to it that was a standard unicast connection. So my question kind of comes, are you really trying to anycast all of your content? Because that sounds very risky based on what I've heard. Or are you anycasting redirections to the actual content involved? And have you looked at any of that root name server research along with this?
I looked at root server studies for a different purpose because RIPE has a very interesting model for the announcements and how they, because RIPE has global instances and local instances, and how they manage to make sure that their global instances don't get majority of the traffic and they can absorb local traffic into local ones. Looked at it from that perspective, but not from this. The general idea is that, a side note is that the performance of these root servers are not the same. The performance of these nodes are not the same. So it is extremely important to land on the right cluster. It's a bigger problem with the GTLD than what it is with the root servers. Because GTLD, if you look at individual GTLD responses, they're very different, especially the node that runs out of Japan. It's not a match for the rest of the nodes. Long-lived TCP connections, yes, the risk is there. We do a little bit of the inside trick on how to make sure that the connection, as long as it's within the same POP, gets to the right server. even after the internal changes that we make to the POP. Our traffic distribution is based on multiple layers, but AnyCast is primarily the way we route the objects inside one region. And I agree with you. Any change over a long-lived TCP connection can make this happen. But I wish I had that chart. It's very amazing when we looked at the TCP data and we looked at the total bytes that were transferred into each connection. Internet is amazingly very small. Let me give you this metric. More than 82% of all the connections that we serve, they fit into one TCP burst. So the client never goes back to actually request the second burst. Yes, if it's a 600 meg file and you span it over minutes and hours, and any change in the network happens, yes, you'll end up going to the wrong POP. But this is surprisingly a very, very small percentage at the very long tail of the connections.
All right. Since there's no one else up here, I'll make my one other comment, which was buried in the details of why that packet too big message comes back is actually a subtle difference in V6 that I think many people haven't gotten their mind around yet. And that is in V4, we can send out a packet that is 1,500 bytes and allow it to be fragmented. And if there's a tunnel, it will go on its merry way. In V6, there is no fragmentation at intermediate nodes. And so you will get many more packet too bigs in V6 than you have gotten in V4, particularly with the tunneling situation, which really accentuates this problem. It also accentuates the standard black holing problem of people filtering packet too big and stalling. And so studying both of those on the V6 and comparing to V4 is interesting. I'd like to see more charts about that.
Sure, sure. Thanks for mentioning that. It's a good point.
All right, thank you, Hossein.